Okay, so this will be our introduction to thermochemistry. It'll kind of get us used to the terms and of the various techniques, and then you'll have later videos where we talk about how to do problems. So, thermochemistry. There are 3 sections to this chapter in your book: energy basics, calorimetry, and enthalpy. So, we've all seen somebody light a match, and we know that when we run it across that rough surface, it starts a reaction that will give off energy in the form of heat and light. So, energy basics. The chemical energy, and you can read this on the screen. What I see is important about energy in terms of chemistry is that thermochemistry is the study of heat absorbed or released during chemical and physical changes. And so if we're doing a reaction, or if, let's say, we're taking something from -5 degrees Celsius like water and bringing it up to the melting point, we're changing the temperature. And then if we take it from 0 Celsius as a solid to 0 Celsius as a liquid, that's a physical change. And then we can go on and raise the temperature of that water maybe to the boiling point, and then convert it from water to steam is another conversion. And we have ways of calculating all of those values. So energy is something we use every day. When you take in food, your body converts it into energy. It breaks down the components and gives you energy in the form of typically glucose, which then can be burned for energy. We put fuel in our cars if we're driving, and that is what gets us to school and to home and to work or wherever we need to go. So we see energy in action all the time. So there are 2 main types of energy: potential and kinetic. An energy definition, you are going to need to know that vocab word, is the capacity to supply heat or to do work. We are mostly interested in the type of heat for this chapter. So potential energy is the energy of position, either because of its composition, like the bonds in something, or its position in terms of it's higher or lower, it'll have higher potential energy. And kinetic energy is the energy of motion, and that's like water flowing has kinetic energy. So here we have a picture, and if you look at the panel A, we see that this is actually Victoria Falls. The water at the top of the waterfall has more potential energy than the water at the bottom of the falls, and the water going over the falls actually has kinetic energy. And so we can harness that energy using turbines, as in panel B. That looks to me like it's Hoover Dam, and we can run that water through turbines, which will generate electricity just by moving it from a high position to a lower position. So you should know the law of conservation of energy, that in a chemical change or a physical change, energy is neither created nor destroyed. Thermal energy is a type of kinetic energy. It's the random motion of the particles, and as something gets hotter, those motions increase, or it has higher thermal energy or faster moving particles. If something slows down, then it has lower thermal energy or it is cold. So in these 2 pictures, we have hot water and cold water, and the hot water molecules are moving faster, so they would have higher kinetic energy and they would have higher thermal energy. When we measure energy, we use a thermometer, and there's basically 2 types that you'll come across. And in panel A, we see that the liquid in that thermometer will expand or contract in a regular manner based on the temperature. And so as the temperature increases, the liquid expands, which will make it rise further up in the column, and that will give you a higher temperature reading. Something like a digital thermometer that you have to make like a temperature probe typically works on part B type of thermometer, where you have 2 metals in contact with each other that have a different amount of expansion they undergo as temperature increases. And you need to know those differences, and they can calibrate a thermometer so that they know how much one over the other expands, so that coil will expand or contract based on the temperature, and you get a reading that's digital on your temperature probe. So, some more terms you need to know. Heat is generally designated as Q, and it's a transfer of thermal energy that are at different temperatures, but they are in contact with each other. And heat flow is somewhat redundant, but it is commonly used, and it means that the thermal energy will flow from the higher energy body into the lower energy body, so that they will come to a thermal equilibrium or the same temperature after being in contact. When two substances are placed in contact, thermal energy always flows from the higher temperature substance to the lower temperature substance. That's the definition of thermal heat flow. So here we have two objects, H and L. H is higher in energy or higher temperature than the L, which is lower. We put them in thermal contact, and now we see energy is flowing from H to L, and then eventually H and L come to the same final temperature. So matter undergoes chemical reactions and physical changes that release or absorb heat. So if something releases heat, like the match at the beginning, that's an exothermic process. If something absorbs heat, that would be something like a cold pack that you can snap the ampule and you mix the two substances together and it gets cold. That's a chemical ice pack, and that would be an endothermic process. Here we have an example or showing you the two. And actually the one on A is an oxyacetylene torch, and the other is the cold pack that you can see in any kind of first aid kit. So there are a couple of different units you need to know. Historically, we have used the unit of calorie, and 1 calorie is defined as the amount of energy required to raise 1 gram of water by 1 degree Celsius or 1 Kelvin. The calorie with a capital C means the type that we use in terms of food calories, and those are actually a kilocalorie. It is very confusing that the capital C means kilocalorie and the lowercase c means regular calorie, but nothing I can do about it. For SI, we use the unit joule, and you can convert from joules to calories and back and forth. The joule is defined as the energy used to force 1 Newton to move 1 meter. And so 1 calorie is equal to 4.184 joules, and so you could convert between the two. Some of your worksheets will be in calories and some will be in joules, so you need to be familiar with both of those terms. So one way we can talk about energy, and I don't like how they have it written here, but the heat capacity of a body is the quantity of heat that it absorbs or releases when it experiences a temperature change of 1 degree Celsius. And so heat capacity is an extensive property. That means it matters how much you have. For example, the heat capacity of a large cast iron pan is greater than the heat capacity of a small cast iron pan. Iron has the same heat capacity, but the heat capacity for this is based on 1 gram. And so our calculation is going to use a slightly different formula. And so specific heat capacity, and you'll see that I'm going to use C sub P because that's the way I learned it way back when. But the specific heat capacity of a substance is typically C sub P, and it equals the energy required to raise 1 gram of a substance by 1 degree. And so we can actually go in the lab and measure these things. And you're going to start out with a lot of calculations. We will do a calorimeter lab, which is kind of fun. So, specific heat capacity for a large cast iron pan and a small one are identical because they're made of the same substance. So, here are some substances. You don't have to know any of these specific numbers. I will give you those numbers as you need them. So, just letting you know. And these are in joules per gram degree Celsius. Some of your tables that you're going to use are in calories per gram degree Celsius. So that is the way I like to see the formula. Q equals C sub P times mass times change in temperature. And to do change in temperature, it's always final minus initial. So if something is gaining energy, then the temperature change will be positive, so Q will be positive. If something is losing energy, final minus initial is going to be negative, therefore Q will be negative, and that will indicate that it's losing energy. So, a flask containing 88.0 times 10 to the 2 grams of water is heated from initial temperature of 21 degrees Celsius to 85 degrees Celsius. How much heat did the water absorb? So you would find the heat capacity on the table is 4.184 joules per gram degree Celsius times the mass times change in temperature, and 85 minus 21 would be 64, and you would get 2.1 times 10 to the 5th joules. Pretty straightforward. And this is really where most of the first worksheet is. So we can use this idea and actually generate energy from the sun, because we can take the sun and heat up a liquid inside the panel, and then that superheated steam would then turn a turbine, which would then generate electricity that we can use. And that's how the ones on the top of a roof work, either at home or out in the middle of the desert. So I'm going to stop here, and we will talk about calorimetry on the next video.